Okay, so it's a pleasure to have Frédéric Touzet from the University of Rennes, who will talk about numerically non-special varieties.
Okay, so thank you for the invitations. I'm very glad to be here. So I would like to present recent work with Georges Pereira and Erwan Rousseau. Which gives the characterizations of non-special varieties. So a straightforward but quite redundant way to define non-special varieties, saying that those are varieties which are not special, but I agree this is not very enlightening definitions. So let me go into further explanations. So this class of varieties, manifold, has been introduced by 20 years ago by Frédéric Campana. And can be defined, characterized in terms of the Bogomolov shifts. Well, more exactly from the inexistence of such sheaf. So let me recall what is a Bogomolov sheaf. So take projective manifold defined over C, and a Bogomolov sheaf is just rank 1 current subsheaf, the sheaf of P differentials on X, P greater or equal to 1, which has maximal chloride dimensions. So maximal among the possible value of the chloride dimensions, which means exactly that its chloride dimensions is equal to P. In fact, once we have such a sheaf, it's defined, there is an associated distributions, which is the annihilator subsheaf of L. And it turns out that this foliations are distributions, a priori only distributions, is algebraically integrable and of codimension P. In fact, the key point is that every holomorphic P form on a projective manifold is closed. In fact, the same holds on compact Kähler manifolds. And well, in fact, these foliations is nothing but Codera fibrations associated to the linear system, which is of sufficiently high power of L. And what is a special manifold? So this definition is due to Campana. simply a manifold which does not admit any Bogomolov sheaf in any degree p. And in fact, typical examples are given by rational manifolds, more generally a rationally collected manifold. In fact, in this case, there is no sections of any tensor power of the cotangent bundle. So a class of example is also provided by abelian variety. And the opposite of special varieties, general type variety. And in fact, Campana has given the following equivalent. That is, X is non-special if only if there exists a surjective map of X onto a variety of general type, but from the viewpoint of orbifold. So the idea is such surjective map exists, you can consider the canonical bundle of V and take the saturations of its pullback. You can recover Bogomolov sheaf. And conversely, taking this remark into account, Bogomolov sheaves provide the fibrations into an orbifold, manifold of general type. And the orbifold structure comes from the ramification locus of a codimensional one component of the base V. And there are several conjectural characterizations of special manifold, which are due to Campana, and which stem from classical Serge-Lang's conjecture. So there is analytic side and arithmetic side.
Can I ask, is bias homomorphism always?
No, in fact, this property is invariant under birational morphisms. So we can suppose that all these guys are smooth up to resolving the singularities and determinacies of morphisms. So a priori, it's just rational. Okay.
The dimension of B is larger than 1, larger than 0.
Well, the dimension and V correspond to the P here. Okay. So there is a series of conjecture from Campana. So manifold should be special. If only if it admits Zariski dense anti-curve. Analytic characterizations, transcendent characterizations. And on the arithmetic side, so save conjecture 1. Well, there are many others. On the arithmetic side, assume that X is defined over a number field. Then this variety should be special. So if only if the rational points are potentially dense, this means that there exists a finite extension K prime of K. Such that the K prime point of X are Zariski dense. There is another concept introduced recently by Ariane Javan-Pecker and Erwan Rousseau, which is also conjectural, which says that X is special if only if X is called geometrically special. Only a conjecture, it's not a theorem. And what's the meaning of geometrically special is a kind of analog of the, the arithmetic conditions, but over function fields. So it should be more tractable than this one, which is as usual something which is out of reach. So geometrically special, I give the definitions. This means that the following, that for every Zariski open subset X on empty, there exists the following triple. C is smooth projective curves. So small c is a point of C. U is a point of our open Zariski subset, such that the following hold. That is, there exists a sequence of morphisms. Of point-in morphisms. set the closure of the union of these graphs is dense in the product of X by C. And it is also somehow the opposite notions of what is called the pseudo-geometric hyperbolicity, which should characterize conjecturally also a variety of general type. Another question is also the following. Sorry. It's a bit noisy. Here's conjecture number 4. Which claims that, well, it's not a claim because it's a conjecture, but so X should be special if and only if it is numerically special. But let us explain this concept of numerically special or non-numerically special. By define what is a numerical Bogomolov sheaf. As before, is a rank-1 coherent subsheaf, sheaf of P differential. Such that this only makes sense when L is pseudo-effective, that is lies in the cone, the closure of the cone of the effective class. Sorry, which has precisely a numerical dimension equal to P. For instance, what is the numerical dimension? For instance, is L is F. Is the top self-intersection power of P, such that LP to the power, L to the power P is non-zero. And in fact, it is maximum possible numerical dimension. This is not completely trivial. In fact, we have the following a series of inequality. First, the Codera dimension of L is so equal to the numerical dimension. This is a common feature for line bundle. But this letter is necessary at most p. This has been proved by Murugan when L is net. And has been generalized by Buxom in the case of pseudo-effective L. And so the meaning is the numerically special. This is just a transpose of a special. That is, X is numerically special. It does not admit any numerical buggable sheaf. Okay.
Is the expectation that a numerical Bogomolov sheaf is actually a Bogomolov sheaf?
No.
No.
No, it's a good question, and we'll give some examples. Okay. Okay. So, in addition, we have the following theorem by Jean-Pierre de Mailly. Which says the following thing. If L L will be always the rank 1 subsheaf. It's pseudo-effective, but not necessarily of maximal numerical dimensions. Then the annihilator subsheaf of L is indeed a Foliations. It is integrable. Okay. So the questions, conjecture is rather obvious when L lies in the differential of a subdegree. Well, following remarks. Also say simplicity that L is the canonical sheaf itself. Say.
By integrable, do you mean algebraically integrable?
No.
Just involutive?
No, involutive.
Okay.
but variety distributions of codimension at least p, not necessarily equal to p. Okay, so when is the canonical sheaf for L numerical Bogomolov sheaf is equivalent to say that L is a Bogomolov sheaf. Well, for instance, if say L is neuf, si c'est conséquence of the asymptotic Riemann-Roch formula. Well, in fact, in numerical lower numerical dimension, the codera and the dimensions and the numerical dimension should coincide. It's one of the main conjecture of the LNP, namely the abundance conjecture. En fait, this fact is a common feature for line bundle. It's so numerically big. It's the same as big. Okay. But in fact, this well, to answer your questions, this abundance principle fails dramatically for degree lower than n. And this can be illustrated by the following example.
I'm a little bit lost the rank of the numerical Bogomolov sheaf because N is supposed to have rank 1, right?
Yes.
So you have rank 0, rank N minus 1.
Sorry.
Because you say that N has rank 1, right?
Yeah.
So the Bogomolov sheaf has rank. It's equal. Sorry, I saw. I thought it was rank N minus 1.
No. It's always one. Okay. Even if the contrary is written, but the rank is 1. Okay. So let me introduce the following examples. Well, the following statement, which is more or less an observations. Take n positive integer, which are equal to 2. So it is easy to exhibit the following object. So that there is a complex projective manifold. Of dimension n, such that the following hold. Then for any p, between 1 and n minus 1, there exists a numerical Bogomolov sheaf. Okay. So such this quadratic dimensions strictly lower than p, even equal minus infinity. So in this sense, this is strongly non-abundant.
Is it known that if we have a numerical Bogomolov sheaf, we have a Bogomolov sheaf, or?
It's conjecture.
Yeah, but like, yeah, if we put together the two conjectures, yeah, but maybe like, is it known as a fact or?
No, it's not known.
Oh,
It's one of the main questions of the paper. But to which we were given answer in the case of Bogomolov sheaf in the sheaf of the cotangent bundle when p is equal to 1. The answer is positive. So yes, natural way to proceed is that well, okay, if the numerical dimension is maximal equal to p, well, the Codera dimensions should be equal to p, but no, not true. Okay. So the idea is that the existence of a numerical Bogomolov sheaf implies the existence of Bogomolov sheaf, which is not the same. Well, it's conjecture, but it's clearly not the same. But in view of this example, which I'm going to explicit now. So the example is the following. So X is will be the quotients of the polydisk of n-dimensional polydisk by compact lattice, torsion-free compact lattice. A co-compact lattice. In the group, or the neutral component of the group of biomorphisms of Dn. In particular, this lattice acts diagonally. It provides many examples which illustrates this principle of non-abundance. So, what is the idea? Simply take, well, start from the polydisk itself, consider the foliations GP defined by the kernel of Z1, P. Because the lattice acts diagonally, these foliations descends on the X. And of course, one can choose well, better to use irreducible lattice. This kind of object exists. Okay, so LP is the LP as the determinant of the conormal of FP. It has precisely a numerical dimension equal to P because it's a natural transverse metric on the transverse factor, which is given by the Poincaré metric. But it fails to have a maximal dimension equal to P because it's minimal foliations. all the leaves are dense. Okay, so if it has colored dimensions equal to p, this means that it will be algebraically integrable. Here it is the contrary. Okay. It is a minimal foliation. So all leaves are dense. So it can be of maximal colored dimension equal to p.
Wait, why is it algebraically integrable?
It's not.
No, but why if the Kodaka dimension is there?
As the thing that I say, because in this case, the foliations has to coincide with the Kodaka vibrations to L. This comes from the fact that every holomorphic P form on the projective manifold is closed. So the fact that all of these are dense, it's related to the irreducibility of the lattice. Okay. So I would like to present two theorems which give some evidence, maybe, towards the conjectural characterizations of special or non-special variety in terms of numerical Bogomolov sheaf. The first one is set under very unrealistic assumptions. I think it is anyway interesting because it gives some insight for the general case. He says the following: that X is projective manifold. Bon, it can be even be compact Keller. So we assume the following. We assume there exists numerical Bogomolov sheaf. Such that the very particular special phenomenon holds. That is, the Chern class of L can be represented by eta. With eta semi-positive, closed. One form such which has everywhere rank P.
Smooth 114.
Yeah, smooth. In general, this guy is only a current, positive current. Okay. So in this case, well, for instance, it's realized by the previous examples. Eta is the transverse Poincaré metric. Bergman metric, which is the product of Poincaré metric on the transverse factor. In this case, the envelope manifold cannot be a special. There exists. Of course, I forgotten to say that in the previous example of the X, X is obviously non-special. In fact, because it's even canonically polarized. Okay. Particular of general type. Well, we'll not really give a proof of this fact, maybe an insight, but one can prove some observations, but which will require some justifications that will not really give. But so the first fact that omega wedge eta equal to 0. So omega is a local generator of L, so it's a P form. Well, this can be improved doing an integration by part using Stokes formula and using the positivity of eta. So this means that underlying foliations, car de L is indeed I mentioned P foliations, which is moreover a transversally Keller, which is invariant transverse metric, which is invariant by holonomy, which is given by eta. And and from this, we can use a technology provided by the theory of Riemannian foliations. Well, there are essentially two situations. So, so I call F the kernel of L. So either F is algebraically integrable, so we can consider the space of leaves, which is well defined, at least as a Keller orbifold. So when we think that the canonical sheaf of this Keller orbifold is correspond to the determinant of the conormal of F. And if we regard this one on the space of Lie, it's positive, okay? The space of Lie is p-dimensional, it's a codimension of F. And so we can use the Codera betting theorem, which is also valid in the setting of orbifold. And one can conclude that L has also a quadratic dimension equal to P. You can take the same L. Okay. And if it's not the case, we can produce representations of the fundamental group of X. In the automorphism group of a certain Lie algebra, which is semi-simple, and which has a dense image. So this Lie algebra is what is called in the theory of Riemannian foliations the Lie algebra of the holonomic pseudogroup, which turns out to be a Lie pseudogroup. And in fact, this is the typical fiber of locally constant Lie algebra of transverse killing vector fields, which locally describes the dynamic of F. And using that, the space of Lie, which is not Hausdorff, but as a kind of negative Ricci curvature, so metric with negative Ricci curvature, we can show this G is semi-simple. Okay? Well, the fact that this representation exists is a common property of Riemannian foliations. Well, no, it's not subjective, but the fact that this one is semi-simple, we use the negativity of the curvature of the metric, which by duality can be turned into positivity of the determinant of the conormal. And this group is a semi-simple real algebra group. So I can use what is known about representations, semi-simple representations, fundamental group of scalar groups. And one can conclude using the results by zero, so which has been precise recently by Campana, Clodon et Sidieux. That there exist surjective morphisms onto an orbifold of general type. And okay, so this means by definitions, by Campana theorem, that X is non-special. That's general type vibrations.
From this case, do you get a map to apply this quotient?
Sorry?
Do you get a map? I mean, in this second case where you have, where the Foliations and
Yeah.
Algebraic, do you get a map to a polydisc quotient?
To policy questions. No. Well, I can get can have further information of this kind of foliations. In particular, one can prove that it's in sense transversally modeled on the bounding symmetric space, but that's all. Huh? Well, okay, but you're right. I don't know how to construct such examples which does not involve the lattice. Particularly, I strongly suspect that these representations given here should be of arithmetic nature. There's a lattice somewhere, I suppose. Okay. So in the previous examples, as the locally constant chief of a Killing vector field, which is what C on the Dn is a constant chief of infinitesimal isometric, the transverse factor, and which descends on the locally constant chief, the cosines. The way to visualize this, the previous example. And okay.
Relation between F and L.
Well, there's no direct relations that we have that we construct is representations of the fundamental groups. So we can prove that F is the pullback of the foliations, which lives here. Okay. Okay. So the fiber of these morphisms are contained in the leaves of our original foliations. And our foliations descend to a foliations on the manifold or bifold of general type. Okay, so the okay, so we said the second theorem. But, sorry.
L is contained in a bogomol of.
No, certainly not. No.
Because you don't know anything about the dimensional tree.
Exactly. Yes. Well,
There's no relation.
I mean,
well, think to this example. So the second theorem is more satisfying. It concerns uniquely a numerical Bogomolov subsheaf in the cotangent sheaf. Without any assumptions of like before, only the assumptions. So the only thing we know a priori is that thanks to the Mailly theorem, that L, the annihilator subsheaf of L is foliations. Okay. Then we can conclude the following. So X is non-special. Moreover, every anti-curve in X is not Zariski-Nonce. And the third point is that X is also geometrically non-special. Okay, so what's property that we wait for, because in view of the previous conjecture. And so if you recall the previous examples, we can suspect that representations of the P1 has to do something with this kind of questions. And in fact, this kind of thing exactly occur in this case. And in addition, the V, the manifold of general type is specified in this case. And the statement is the following. Well, that's a direct consequence to justify a certain number of points, but this is a consequence of the following properties. So either the codimension, the Codera dimension of A is equal to 1. So this implies by definition that X is not special, of course. So there are fibrations, orbifold fibrations over the sense of orbifold over a curve. The second point is the consequence of elementary de van Linde theory. And the third has been proven by Campana. Okay, in this case, it is okay. So either this is the second point of the alternative. Codera is minus infinity. And we have the following phenomenon. So there exist morphisms of X on two quotients of polynomial by the lattice. Such the foliations, which is defined by the kernel of L, is a pullback of one of the topological foliations on these quotients. So for instance, up to now, remembering the coordinates, we can suppose that G1 is codimension 1 foliations given by the kernel of Z1, which descends on these quotients. Okay. So, well, at this point, we have to care about several things. Well, this is the theorem that I proved 10 years ago. But And yeah, yes, you have to be cautious because of the following fact. The first is that the lattice is not necessarily co-compact, but it's not a big deal. But there is a more subtle issue. Is that this lattice gamma is likely to have torsion element, not necessarily torsion free. If this lattice will be torsion free, this is finished because the image is the general type variety discussions of by definitions. More or less, it is not special. Or for the first point. And well, the point is, we finished in 1 minute. The point is that the foliation which exist here is not has not necessarily conormal, pseudo-effective conormal, okay, because of the existence of elliptic singularity discussions. But the fact that the pullback by assumptions is as conormal pseudo-effective force this phi to be maps in the maps well defined in the orbifold sense, and the orbifold structure here is the discussions of the image of discussions equipped with this orbifold structure is an orbifold of a general type. Okay, so it's a general type orbifold. Okay, in the sense of Campana. In fact, this forces phi to have a multiplicity, to pass from non-pseudo-effectivity to pseudo-effective. It's a multiplicity here, and everything works fine. Okay. So this proves the first point. And the other points we use also the precise descriptions of these guys. Not enough time to go on, but this is the point. It's not only an orbifold of general type, but it's a very precise description of the questions of the polydiscs. Okay. So I finish here.
Are there any questions or remarks? I have a question.
Yeah.
According to the first point of the Campana conjecture, X is special if there is a single analytic map from complex numbers that is Zariski closed. It reminds me about Green, right?
No.
Zariski does.
It's special. Okay. Well,
yeah. Okay. Yes. This reminds me about Green-Griffiths line conjecture, which is similar also about analytic maps from C. And,
of course.
And therefore, I have a question. Could we have a situation that a single map is not enough to be to have a Zariski dense image, but there could be many. So a variety that is not special, but has many maps that together give us together the image give us Zariski dense something.
But it's conjecture that it can't occur. But it's a consequence of the Green-Griffiths law, the conjecture. Well, on the orbifold of general type. Okay.
Yeah, but
If it is not special, it must fiber over an orbifold of general type. And so you take any anti-curves on X. So okay, it's going to project on the orbifold of general type. So conjecturally, it should be localized in the proper analytic subset of this.
I think this question is about the fact that there could be infinitely many anti-curves, such as the union of the images with Aristoteles. Of course, this can happen with data product.
Okay. So see, of course.
So you have infinitely many C1, so infinitely many anti-curves. And the union is Aristoteles.
But if you ask the question for pointed anti-curves,
That was the answer, yeah.
okay. I think we are one. I'm sorry. As far as I'm concerned.
Okay, any more questions?
Are these conjectures known in low dimension? For instance, this would imply that it's true in dimension 2, right? But
Yeah.
are these things
Yeah, that's a very good question. For instance, the next step would be to study the case of 3-dimensional. When we have a foliation by curves, the determinant of the conormal is as a maximum numerical dimension. So we had discussed about this with my co-authors. But, it seems doable, but bon. we have not a definite argument.
Okay, so if there are no more questions. We leave here maybe 6:45.
Yes.